Hello, I'm back with the second part of the 2022 NJA, so Advanced Maths, Advanced Physics, 20 questions, starting with this one, 21. Find the value of this integral. We've got two terms on the numerator and one on the denominator, so it's right for splitting it into two fractions, isn't it? So I'm going to have 2x to the half minus 3x to the minus 3 over 2. That's the thing that I'm integrating. So I'm going to have to do a 4 over 3 to get that coefficient. Okay. And then I'll need a 6, and it's going to be a plus to the minus a half. Okay. Put the 4 in. I'm going to have an 8, so 32 over 3. And then I'm going to have a 6 over 2. Then I'm going to take off a 4 over 3 and I'll take off a 6. Okay, so that is 10 and 2/3 plus 3 minus 6 minus 1 1/3. So I'm taking 3 off, 4 off, and a third off. 6 1/3 is A. Okay. 22, we've got a stationary wave. And it's 150 centimeters there for what, 1, 2, 3 wavelengths. So lambda is 0.5 meters. Transverse waves that are creating the stationary wave travel at 300 meters per second. What is the frequency? Well, we just need to double it, and we divide by the wavelength, and we get 600 hertz, which is E. 23. Diagram shows a semicircle, radius 5 units. Okay, that's on the picture, and a triangle. It's got those vertices, which is also on the picture, and that's on the arc of the semicircle. So it's all in the picture. We just want an expression in terms of x for the area of the triangle. Right, so the area, half base times height, is going to be 5y. So that's what we want. We want that in terms of x. Well, we've got a semicircle, so we've got x minus 5 squared plus y squared is 25. So we've got the y squared is 25 minus x squared plus 10x minus 25. Get rid of those, get rid of those. So 5y is going to be 5 times the square root of 10x minus x squared. Actually, that's the answer that's already on the screen. So we've got another A. Stone is thrown vertically upwards from the surface of the earth and reaches a maximum height h. Same stone is thrown vertically upwards from the surface of the moon with the same initial speed. What is the maximum height reached by the stone thrown on the moon? Right, so these are our gravitational field strengths. And, well, we've got the same work done, force times distance. We're reducing our force down. So we need to up the distance accordingly. So it's going to be 10 over 1.6 times h. So we've got another A. That's just the conservation of energy thing. For mathematically similar solids, W, X, Y, and Z have the following properties. We've got ratio lengths, areas, and volumes. What's the order of the solids arranged in increasing volume? Right, so we've got, well, X is bigger than W. We've got that x is bigger than y, okay, but it's much more bigger than w than y. So y is bigger than w, and then we've got that z is bigger than y. So we just need to know what's going on with z and x. Well, x is going to be, by the time we increase these surface areas up, x is going to be bigger than z. So we need to have w, y, z, x, which is B. Okay, that was another quickish one. 26, light incident on a boundary between a vacuum and a medium x as angle theta is shown. Okay. Incident ray is partially reflected and partially refracted. The angle between the reflected and refracted rays is 90 degrees. What is the refractive index of x? Okay, so that's theta as well because it's reflected. So that's 90 minus theta. So Snell's law, we've got that sine theta times the 1 is what we're looking for, n times sine of this, which is cos theta. So n is tan theta, which is E. Right. 27. Which one of the following expressions is equal to this? So we've got square divided by cube. Okay, so I've got 4 plus 4 root 20 plus 20 divided by, well, let's leave one of the brackets off to the side and do the other two. So that's going to be a 1 plus a 5 is a 6 plus a 2 root 5. I can get rid of some 2's. And then I'm going to want to rationalise, which would be a 3 minus root 5 I'm going to be doing, top or bottom. So I've got a 12 plus 2 root 20 times 3 minus root 5. So what's that giving me? 36. And then I'm going to have minus 2 lots of root 100, so minus 20, plus 6 root 20, minus 12 root 5. That's what I've got on the top. And at the bottom, this is now a 3 plus root 5 times a 3 minus root 5. So that's going to be 4. And I've still got the 1 plus root 5 knocking around as well. So I've got a 16. I've got a, well, I can take a root 4, which, oh, they just cancel. They're the same thing. So that's good. So I've got a 16 on top, and I've got that 4. So I've got a 4 over 1 plus root 5. So 1 minus root 5 on the top, which is going to give me a minus 4 on the bottom. So that goes, and I get root 5 minus 1, which is yet another A. I mean, we've had like 4 or 5 A's already in 7 questions. An electric train is travelling along a straight horizontal track. It passes a point Q on the track at time t is 0. Distance x that it then travels away from Q is given by that equation. A and B are constants. So that's a sort of S equals ut plus half at squared type affair where we'd have a constant acceleration. Which of the following statements are correct? Speed of the train increases with time at a constant rate. Well, that's going to be true because we've got that constant acceleration. Essentially, I'm saying that d2x dt squared, which in this case is going to be what, 2b. So we've got a constant acceleration. So we're going to have a constant increase in the speed of the train. The resulting force acting increases with time. Well, no, we have a constant force for constant acceleration. Rate at which energy is transferred to the train increases with time. The rate at which energy transferred to the train increases with time. Well, yeah, it's getting faster and faster. And if we're increasing the velocity linearly, and our energy is then proportional to the square of that, then that must be increasing the rate of energy transfer. So where are we? 1 and 3, F. Okay. So 29, evaluate these things. Right, so sum to infinities. So we're going to have a half over 1 minus a half, but then we haven't got the first term, minus a half. Then we're going to have a third over 1 minus a third, minus a third. And then we're going to have a quarter over 1 minus a quarter, minus a quarter. Okay, so that is a half for that first bit, because we've got a half over a half minus a half. Then we've got a third over 2 thirds, so that's a half minus a third, so that's a sixth. And then we've got a quarter over 3 quarters, so that's a third minus a quarter, so that's a 12th. So we've then got a half and a sixth and a 12th, we've got 3 quarters, so B. Okay. Length of wire, resistance R. Another length of wire made from the same material is twice as long and half the diameter. Both wires have circular cross sections. 2 wires are connected in parallel. What's the total resistance? These 2 wires in combination. Right, so the resistance is going to be this if we've got the same material. So if the length goes up, twice as long, so that's times 2. The diameter is half, so we're going to be getting a times 4 on the area. So we've got 8 times the resistance. So we've got a 1 resistor, 1 ohm resistor, or 1 R resistor, and an 8 R resistor in parallel. So we're going to get 8/9 of R, which is B. One of those quick parallel calculations for resistors. What is the complete set of real values of x for which that inequality holds? Okay, so we could say, well, let's have that y is equal to x squared. So we've got that y squared plus 4y minus 21 is less than 0. So that's going to be y plus 7, and then y minus 3 is less than 0. Well, it doesn't work for this. So we need we're looking for stuff which is between these points because it's a positive quadratic. So we're looking at this one then. So we need x to be between minus root 3 and root 3, which is a. Again, another a. Empty bucket has a mass of 1.2 kilograms. Internal volume of that. Bucket is used to lift water from a well. Bucket is attached to a light, inextensible rope which winds onto a rotating cylinder of radius 0.2 meters. Right, to lift a bucket completely full of water at constant speed, it's necessary to apply a force 250 newtons to a hand. Guys, there's a lot in this, isn't there? Of radius 0.6 meters. Energy required to lift the bucket is wasted energy. What is the efficiency of the system in lifting water for the well? Right, so if we do one rotation of the handle, so we're doing 250 newtons times 2 times pi times 0.6 meters. So that is our in. That's what we're putting in. And what we're getting that's useful out of that is we're getting a bucket load of water, which is going up by, right, 0.2 meters is the handle, not the handle, the barrel, 0.2 meters, right? So we've got a 2 times pi times 0.2, but we're lifting a bucket full of water. So that is 0.015 times 1,000, the density of water. So that is giving us 0.015 times 1,000, but that gives us the kilograms. So we have to multiply by 10 to get the newtons, to get the weight. Right, and then we need to divide the bottom one by the top one. So anyway, what have we got here for all of these? We've got 1, 2, 3, 1, 2, and then 3. So that gives us 15. So we've got 150 times 10. Oh no, 150, I've done that 10, times 2 pi times 0.2 over 250 times 2 pi times 0.6. Okay, so they're cancelling. Get rid of those. We've got a third of that, which makes it 50. So we've got 50 over 250. So we've got 20%. That's not very good, is it? But still, see. Bit of a crummy setup for getting that water out. Sector of a circle has perimeter 24. For what value of the radius does the sector have the maximum possible area? Okay, so the perimeter of a sector is going to be 2r plus r theta. We've got theta in the middle, and that's 24. And then the area is half r squared theta. So we want to get rid of theta. So we're going to have that theta is 24 minus 2r over r. And stick that into here. That half is going to come into effect. And so is the r. So I'm going to get 12. How many r's have I got in all of this? I'm cancelling that r with that r. And that with that. And that is the 12. So I've got 12 minus r multiplied by r. And that is, yeah, that's all I've got really, isn't it? So I need dA dr is going to be 12 minus 2r. So these things have to be equal to 0. So I've got that r is equal to 6, which is d. Okay. Uniform meter rule, mass 100 grams, 1 meter long. Small object at one end, small objects at the other end. It's balanced on a pivot. When the ruler is balanced, what is the distance of the pivot from the 0 centimetre mark. Okay, so we've got this. We've got 20, 180. So we could just do, well, I'll do 2, 10 and 8, just to get rid of anything else that's going on. Well, the pivot's going to have to be somewhere on this side. Can't be on the other side. It's got to be going towards the 8. So let's say that is at x that we're trying to work out. So I'm going to have 2x, and then I'm going to have a 10 lots of x minus 50, if I do it all in centimetres. There's got to be equal to 8 lots of 100 minus x. I think that's right, isn't it, all in all? So I've got 2x plus 10x is 12x, minus 500 is 800 minus 8x. So I've got that 20x is 1300. Bomb, bomb, 65. E. 35, the curve that intersects the x-axis at the points A and B, minimum at point C. Okay, looks like I'm drawing a rectangle on that, so let's put that out. So that's going to have points at, well, intersections at 3 and minus 2. So it's doing this. We've got the point C is at the minimum, which is going to be when x is a half. Okay, we've got the rectangle ABDE. It's got one vertex there, one vertex there. C is on the other edge between D and E. Okay, so we've got a rectangle that looks like that. We want the area of the rectangle, right? So we've got 5 going that way. So when I put x is a half into here, I get a quarter minus a half minus 6. So that's minus 6 and a quarter. Okay, so I want to do 5 times 6 and a quarter, which is 30 plus, well, 31 and a quarter, which is D. Okay. 36, circuit comprising 2 resistors, 2 batteries, negligible internal resistance, set up as shown. Oh, we've got the old opposing EMFs. What's the magnitude and direction of current in the 3-volt battery? So do the usual thing. Let's think a bit with one battery in place and the other one not there, and then vice versa. So if we were just going to think about the 6-volt one, so let's do the 6-volt one first. Essentially, we're short circuiting the 3 ohm. So we're going to end up getting 6 amps going that way. So what if we then had the other one? Our total resistance that we're going to have on this is going to be 3/4, because we've got the 1 and the 3 in parallel with each other. So if we've got 3/4, we must have 4 amps going the other way. So add those up, we've got 2 amps going to the left. Well, they've gone a direct, so 2 amps going from Y to X, which is F. Okay, that was one of the more friendly opposing EMF ones. Straight line passes through those points. What is the perpendicular distance to the point P from that line? Oh dear. Right, this is positive constant for A. So let's just look at this quadrant here. So we're going through 0 to A and A 0. So we've got a straight line going through these. And then we've got a point P up here, and we want to get that distance there. Okay, so this has got a gradient of -2. This will have a gradient of a half then. That's going through A to A. So let's get the intersection. Maybe there's probably quite a few different ways you could do this. So for the first line, I've got that y is going to be -2x plus 2a. So that's what I've got there. And the second line is going to be y minus 2a is going to be equal to a half of x minus a. So actually the y minus 2a's are sort of similar here. I've got minus 2x is a half of x minus a. So minus 4x minus 5x is equal to minus a. So x is a over 5, which means y is going to be, oh, this is still horrible looking, isn't it? So I've got 2a minus 2/5 of a. So I've got 1 3/5 of A for Y. And what am I trying to do again? I'm trying to get this distance here. Okay, so that's that point there. So my change in X here is 4/5 of A. My change in Y here is 2/5 of A. So Pythagoras it up. I can take those 5s and A's outside. So I'll have an A over 5. And then I'm going to have a root of 20. So 2 root 5 over 5, C. Okay. I've gone too far. 30, whatever number that is. 8, is it? Is it 38? Not really matters. Yeah, 38. Two isolated spheres have masses m and 2m. They're moving towards each other along the same straight line speeds 4v and v. They collide and coalesce. What's the loss of kinetic energy? Right, so conservation of momentum then. So say they were going to move at u afterwards. We've got more momentum going that way. So let's say that was u afterwards. Not that it really matters, but we've got 4mv plus minus 2mv is equal to 3mu. So we've got, get rid of all of these things. So u is going to be 2/3 of v. So we've started off with m over 2 times 16v squared plus m times v squared. So that's 9mv squared. And we've gone to 3 over 2m times 4 over 9v squared. So we want the loss, we want the difference between these two things. So that goes away and becomes a 2. That goes away and becomes a 3. So I probably shouldn't have squared the 2/3 because it's just come back to 2/3, isn't it? So I've got 8 1/3 is the difference between those. 8 1/3 mv squared. So where's that? Is that C? It is, isn't it? C. That's 8 1/3. Okay. 2 to go. Find the sum of the real solutions to that equation. So we've got 2 to the x, 2 to the x over 2. Let's write this in better powers. So that is a minus 2 to the x over 2, but then I've got also a 2 to the 3. So I've got an 8 there. Okay. I mean, that looks like I've got 82, so let's write that out a bit better. 8 times 2 to the x over 2 plus 12. And that's got to equal 0. So let's say that y is 2 to the x over 2. Y squared minus 8y plus 12 is 0. So I've got a minus 6 and I've got a minus 2 is 0. So if y is 2, then that is 2 to the x over 2. So, well, x would have to be 2. So that's thing. It's one of them anyway. And then if y is 6, then I've got that 2 to the x over 2 is equal to 6. So that's going to be log base 2 of 6 times 2 is x. So I want to add those together. So I've got 2 plus 2 log base 2 of 6, which is none of the answers, but it could be the last one. Could be the last one, because that's going to be log 6 is log 2 plus log 3. Log 2 is 1. So I'm going to get 2 plus 2 plus 2 log 3 base 2. So that is F. Okay, they nearly sort of snuck off with a tricky one there. Steel cable, mass 64 kilograms, cross-sectional area of that. Oh, Young's modulus, okay, nice one to finish on. We've got all of those. When the cable lies horizontal on the ground, it's that, so that's our L. What is its extension when it is suspended freely from one end and hangs vertically? Right, okay, these ones are sneaky. I've seen this sort of question before. When you first see these, they can be quite tricky, so I might take a bit more time on this one, because you can think about these in a number of ways, because usually when we're doing Young's modulus stuff, right, so I'll answer it the way that I would normally answer this one. having thought about it in the past. Normally when we do Young's modulus, you get yourself your material and you lay it on the table and then you stretch it. So we've got some kind of force that we're applying to a bit of material, and we're not concerned about the weight of the material because we're just stretching it sideways. So they're trying to throw us off our guard here by saying, okay, well, let's just have it hanging downwards because the weight of the material itself is the thing that's stretching it. So what you can do is think, okay, if it was just hanging straight down, well, let's just reduce it down to some mass at the center of mass and say, okay, right, what we're really doing is we're applying a force equivalent to the weight at the halfway point of the material. So in this case, we're applying 640 newtons halfway down. So let's turn it on its side and do the same thing. So let's take 640 newtons and apply it at the midpoint, in which case we've now got 20 meters for our L. We've got our F is 640 newtons. So that's all fine. We've got our cross-sectional area and we want the extension. So we're doing F times L over A times our Young's modulus is what we want for extension. So that's 640 times 20 over 2 times 10 to the minus 4 times 2 times 10 to the 11. Okay, so what have we got here for positive tens? Well, I can get rid of that 2 and that 2. We got 1, 2, 6 tens, and then a minus 11. So we've got a 10 to the minus 5 there, which leaves us with a 32. So 3.2 times 10 to the minus 4 is going to be the answer, which is just nipped out as being G here on the bottom. So that's one way of doing it, having seen this sort of thing before. You've got other ways of thinking about it, like when it's hanging down under its own weight. So the weight's acting in the middle here. So the further you are at the bottom, like if you're at the very bottom, like imagine slicing this up. You get all of this and you chop it up into your, like your DHs or something, or your DYs, DXs, whatever you want to do. If you're in the very bottom slice, there's nothing pulling it downwards. You're not getting any extension there. At the top, you've got the full effect of the 640 newtons pulling it downwards at the top. So you're getting full extension at the top. In the middle, you're getting half. You're getting this sliding scale from top to bottom of 640 newtons there down to 0 newtons at the bottom. So we could just say, well, our average force then is 320. So we could jump straight into doing this, but with the X, and say, well, yeah, let's use the full length of 40, but then have our force of being 320 because we're halving it down. Now you could do it that way. And you can see how this lends itself to doing calculus on it. So especially if you had a variable density or something like that going through the cable, then you could integrate how the weight is distributed from top to bottom of the cable, and then integrate through. But really, you could do either one of these methods. I mean, it's quite nice just saying that the average force is 320. So we do 320 times 40 over 2 times 10 to the minus 4 times 2 times 10 to the 11. So those cancel with that 4. And then we've got 1, 2, 3, 7 with 11 to come off. So 3.2 times 10 to the minus 4 again. So yeah, different ways of doing the same thing. It certainly helps having seen a question like that before. But yeah, this is the sort of thing we'd do if we were in the lab, and it would put it sideways and have a more controlled force applied to it. So anyway, that's wrapped up those 20 questions. Again, another quite nice bunch. That last one was quite difficult. Question 40. 37 was time consuming. There might have been a better way of going about doing that. The opposing EMFs was quite a friendly one. So yeah, it's the usual sort of thing. I mean, they're quite nice questions. Okay, that was a little sneaky, wasn't it? 32. So maybe these ones were a bit more difficult than the 2021 year, because 2021 did seem to be quite an easy one, comparatively speaking. But still, that's another one done.